Alright everyone, welcome back. This will be an example video using the principles we've covered up till now. So in part A, we want to find the magnitude of the gravitational force on this mass of lowercase m, right? This small mass due to this ring of mass capital M. And so, by the way, this ring is of radius capital R, and the central point is a distance x away from the lowercase mass, right? And that mass is directly above the central axis, right? Right there. So this configuration, it may look a little bit strange, but it does occur more often than you might think, right? Especially in astronomy. There are rings around planets. There are rings around even galaxies, right? And sometimes other foreign bodies may come around and in the neighborhood and be attracted towards that ring. Okay? This is a pretty idealized case in that it's not moving and it's directly above the center, but the principle is still the same. Right? So in part A, we want to find the magnitude of the net gravitational force on this mass over there. Okay. Part B, we want to find the speed from that gravitational force, the speed that the mass passes the central point. Okay. All right, so in part A, well, this being a gravitational force, there has to be an attractive force between two masses. So that means that the force will be directed through that line right there. So let me redraw this situation down here. Okay, there's that ring, kind of mass R, and then there's the particle out there, mass M. All right, so because this ring has a mass, capital M, the force will be directed actually along the line from center to center. And by center to center, I mean you can think of this ring, which is really a giant ring of continuous mass. Well, think of breaking up that ring into tiny chunks, right, of mass dm, right? Every atom, every chunk in this ring has a gravitational force on that particle over there. Okay? Every particle in this ring is trying to pull that mass towards it. So this particle up here is trying to pull it that way, right? This particle here is trying to pull it that way, etc., around, even that particle down there. Okay? And they're all acting at the same time simultaneously. Also, it's good to note that this ring is circular. So it's a constant radius r around, and that's important because let's take a look. If we were to draw the vector, the vector bars rather, the gravitational force will be directed like that and like that, right? Equal magnitudes in all directions. I'm only drawing two for illustration's sake. But if they're equal magnitudes, again, because that ring is circular, let's take a look at the components. We have a component this direction. Actually, let's not use red. Let's go back. Let me use black. Can you see what's going to happen? There's a component of the force up and a component down, right? Those two really are the sign components, and they will cancel out. The only components that don't cancel are the components like that, right? That point directly towards the center. So in fact, they add up. They combine to give us a net force. What component is that? Well, let's call that theta. And so that means that in red, those are the cosine components. So the force of gravity times cosine. That's what those are. And by the way, this is F sine. Okay? So, the magnitude of the net force, well, it's just the magnitude of Fg cosine. So let's see what that is. In part A, here we go. We have the net force is really Fg cosine. That's it. We're not worried about the acceleration yet, just the magnitude of that force. All right, so really I guess we just need there. Don't need the vector bars. So this turns out to be GMM over r squared times cosine. In terms of our problem, what is cosine? I forgot to mark this as x. Well, remember that cosine is the adjacent over hypotenuse. So in terms of our problem, the adjacent to this angle is this length right here. That's x. The hypotenuse, we haven't really called it anything yet, so let's just call it lowercase r, right? The general distance variable. So x over r. So now plugging in x over r, right, up there, we get the following. GMM times x over r cubed. Okay, that looks a little strange, but it works out, I promise. All right, what is r? We don't really know that distance, right? But this forms a right triangle. The radius of that ring and the central axis distance. That forms a right triangle. So really we could figure out r. R is the square root of x squared plus capital R squared. So now if we plug that in, we get the following. GMM times x over, that's a square root cubed. Well, that's the same as r to the 3/2. And now we know everything in that expression. G is a constant. The mass of the ring, it's right there. The mass of this object, right, the lowercase m, it says it's 84. X distance, problem says, is that, right? And r, we can figure out because we know both of those. So plugging in everything, being mindful of your parentheses and exponents, we should get a fairly small force, 0.00014 newtons. Not a very big force at all. But if we're in a vacuum, and even though we're separated by, right here, by 100 million, by 660 million meters, there's still some non-zero force, which, yes, will cause some non-zero acceleration, which leads us into part B, right? So that means this object out here will start to creep towards the ring and accelerate towards it. So in part B, we want to find the speed at which it passes through the middle of that ring, right? So if we go back to the picture now, we can use conservation of energy, right? This is in a vacuum, so no energy is lost due to friction. So we can take the energy at the start when it's at a distance of x away and the energy final when it's passing through the middle. All right, now again, these are considerable distances and the force of gravity is not constant, okay? It changes. So initially, kinetic energy is 0. It's starting from rest, right? Yep, starts from rest, right there. So there is no kinetic energy initially, but there is some gravitational potential energy initially. The initial distance is x in this case. All right, right, yeah, x. Well, actually, hang on a second. Let's let me finish writing this out. Finally, 1/2 mv squared at the center minus gmm over the distance. Okay, now this brings up a good point. The distance right there, when it's at the center right here, the distance between the object's center of mass, right, that particle's center of mass, and where the mass actually is, right, that is r. So that's what we need to plug in for the final potential energy. Initially, I need to go back and amend that, because initially the distance in between the masses here and here, for example, is r, right? Remember, again, this is a circle, and so this particle is a distance r from all points, right? From all points. It's kind of a cone, if you will. So that means that, whoops, that is r, not x. All right, so this we can say the speed is final. Now, our strategy is to solve for v, right? The mass of that particle actually cancels out. You see that? Lowercase m, lowercase m, lowercase m, right? So solving this for v, I'm going to take, let's see, I'm actually going to change sides. 1/2 v final squared equals, I'm going to take this term to the other side. So that becomes positive g, nope, no m's, gm over capital R minus gm over lowercase r. All right, so v final is then, let's see, I'm going to factor out the g and the mass. 1 over capital R minus 1 over lowercase r. Again, remembering that lowercase r was x squared plus r squared. Square root. Remembering to square root the entire thing because the speed was squared, right? This will give us a final speed of, well, I should put approximate. What did I have? Approximately 45 meters per second or so, right? Depending upon how you round. About 45 or so meters per second, or thereabouts. So that's a considerable speed, right? But, you know, in the grand scheme of things, it's not that fast, but it is non-zero. It will be traveling some final speed after traveling for nearly, what is that, 1 billion meters, almost 1 billion meters. It'll go from 0 up to 45 meters per second. All right. So in essence, this problem was a straightforward conservation of energy problem, right? But remember, in this chapter, for universal gravitation, when we're talking about these great distances, right, the force of gravity is not constant. So we must use the potential energies as such, right? Minus gmm over r. And remember, it's always the distance in between the masses themselves. All right? Thanks for watching.